Algebra 1 students, welcome to your 6.4 notes. We've spent the last three sections learning different ways to solve systems, graphing, substitution, and elimination. Today we're going to look at how do we use this information to solve real life problems. One thing we have to keep in mind is when we want to choose which method. So you can see the three options listed here in the chart. When you need to see an answer or when you just need an estimate, graphing is a good option. And then with substitution and elimination, it basically comes down to what's easier to do. And so you'll have to make that choice problem by problem, but if you understand the two processes, it should make it to where you could use either, but you might look at one and say, you know, this one looks better, that is a better option than the other. Systems equations are useful for modeling problems that involve things like mixtures, interest rates, and break-even points for financial problems. Now, a break-even point for a business is where income and expenses are exactly equal. We're going to take a look at that in the first problem. A bracelet designer sells his product for $5. Each bracelet costs $2.25 to create. The designer also had $1,485 of expenses to start his company. How many bracelets must he sell to break even? Okay, so what we're going to look at is defining variables, where I'm going to say X represents the number of bracelets. Y is kind of a weird variable in this case. I'm going to say it's either profit or expense. We want these two to be equal, so we're going to use Y. It's almost meaning different things in different situations, but we want them to be equal to each other. So our system will look like this. First, let's talk about profits. Y equals, well, it says we're selling each bracelet for $5. Everything else that's listed is an expense. We're going to list those things here. So our expenses would be Y is equal to $2.25 per bracelet, but there was also an initial expense of $1,485. All right, what I'm going to use on this one is substitution because it's already set up to say y equals 5x and y equals 2.25x plus 1485. So we'll do this, 5x plus 2.25. Excuse me, 5x equals, let's try that again, 5x equals 2.25x plus 1485. I'm going to subtract the 2.25x from each side. So 2.75x would equal 1,485. A little division here. And x equals 540. And the question was, how many bracelets must he sell to break even? And there's your answer. He has to sell 540 bracelets. Two aquariums are being filled simultaneously. An 800-gallon tank has 100 gallons of water and is being filled at a rate of 12 gallons per minute. A larger tank, 1100 gallons, has 200 gallons and is being filled at a rate of 7 gallons per minute. After how many minutes will the two have the same amount of water? All right, we're going to go through the same process we went through last time, where we define our variables. So I'm going to say X represents minutes and Y represents gallons of water. All right, so let's start with the 800-gallon tank first. How much water is in that tank? Well, it has 100 gallons, and we're adding at a rate of 12 gallons per minute. The 1100-gallon tank starts with more, but the rate at which it's being filled is a little bit slower. So there's your system. Now again, I think this problem lends itself to a quick substitution. 100 plus 12x equals 200 plus 7x. I'll subtract 100. And subtract 7x. finally divide by 5. And so x equals 20. And what does that mean? X equals 20 what? Well, it says right here the x represents time in minutes. So 20 minutes is the solution. That's when the two tanks would have the same amount of water. All right. On a nice winter day, it's nice to think about riding a wave runner. That's why this problem was written. So I'm riding my wave runner. It takes me 30 minutes to travel 16 miles downstream. The trip back, though, takes much longer, an hour. My speedometer shows a constant rate of speed for both trips. How fast was the wave runner traveling in relation to the water? And how fast was the river's current moving? And there's a notice there. It says distance equals rate times time. We're going to use this equation quite a lot through this section. Distance equals rate times time. By the way, another name for rate is speed. You guys are used to hearing it that way probably more than rate. All right, so let's set that up using distance equals rate times time. Let's talk about the first trip. And you know what I was about to do was skip an important step I'm constantly getting after you guys about. We need to define variables. Then we can start writing equations. Well, what are the two things we're looking for? Well, the first one is I want to know the speed of the wave runner. And I'm getting these from the last sentence. It's the two things it asks us to find. And then the river's current is the other one. The speed of the water. All right, for the first trip, the half-hour trip, I'm going downstream. So my total distance is given to us as 16 equals, and then the rate, the speed. To find the rate when I'm moving with the current, I basically add the wave runner speed and the river speed together. They're going the same direction, so we'd add those two together. That would give me my total speed. Now it says it takes 30 minutes, so I'm going to put this in terms of hours and do 0.5 right there. The return trip is the exact same speed. Now here's where we have to think about this. This time we're going against the current, so we would go x minus y, and this time the trip takes 1 hour. Okay, I'm going to go ahead and simplify these two equations. 16 equals 0.5x plus 0.5y, and 16 equals x minus y. What I'm going to do is multiply the first equation by 2 and rewrite it down here. So 32 equals x plus y. We can add those two equations together, divide by 2, and x is 24. Now I'm going to plug that back in right there. X minus y equals 16, so I know 16 is equal to 24 minus y. So negative 8 equals negative y, so y would have to equal 8. All right, the key to a problem like this is to make sure you write your answer in a way that actually makes sense. So I'm going to do that over here. I'm going to say the current was 8, and that's going to be in miles per hour, where the wave runner, this was our x value that we found first, the wave runner was traveling at 24 miles per hour. All right. Miss Carroll invested $1,200 into two separate accounts at the end of 1 year. Account A had earned 8% interest, account B 11%. She'd earned a total of $117 of interest. How much did she invest into each account? Okay, in this case, what we're going to look at is we first need to define variables, and I'm going to say X represents money in account A, and Y is going to be money in account B. The first sentence tells me my first equation. It says Miss Carroll invested $1,200 into two separate accounts. X plus Y equals 1,200. That equation right there lets me know nothing about interest. It's purely about how much money she put into the accounts at the beginning. This second equation is where we'll deal with interest. The first account gets 8% interest, so I'm going to write that as 0.08x. The second account is 11% interest, so we'd write that as 0.11y, and the total interest earned is $117. That model right there is what you're going to see virtually every time you do a problem like this. Now, I'm going to let you choose your method. So pause the video, go through and solve for X and Y, and then when you hit play again, you can see the method I chose. Welcome back. You can see I chose substitution by solving the first equation for X, plugged in that value, I went through, and that allowed me to solve for Y. And then I substituted that answer back in for y here, x plus y equals 1,200 to get x. So in the end though, I need to go ahead and write exactly what my answer means. So what we know is that Miss Carroll invested $500 in account A and $700 in account B. You always have to put these kind of things in context, make sure that they make sense and that they answer the question that was given to you. All right, we have one more to look at. Mr. Thornburg is using his slightly above average math skills to assist the Olathe South Science Department. The chemistry teachers need 90 liters of 8% hydrochloric acid, but they have only 6% and 12% solutions available. So Mr. Thornburg is helping them figure out how much of each they need to mix together. All right, define variables. X is going to represent the number of milliliters of, let's go 6% solution on this one, where Y would represent the milliliters of 12%. So we're talking X and Y represent volumes. How much of each mixture? Okay, first thing I notice is this. It says they need 90 liters. Right there is your first equation. X plus Y equals 90. The second equation is the one that tends to bother people a little bit. It's when you have to include percentages. I think most people can understand why I write 0.06x plus 0.12y. That represents the 6% of the milliliters of the first solution, and then 12% of the second. But here's the part that gets people. This equals not just 0.08, but 0.08 times 90. This equation right here is the amount of pure hydrochloric acid we're dealing with. 6% of X, 12% of Y, and it has to equal 8% of the 90 liters. And I just realized I wrote milliliters for my variables. This doesn't change our equations, but that's actually liters here, not milliliters. Significant difference. Okay, I would encourage you to use substitution. Again, I'm going to pause it. You pause it as well, do the algebra, and then check your answer to compare with mine. Okay, you can see my work here. As I said before, I'm using substitution. I found that y was 90 minus x. I plugged it in right here to this equation, rewrote it here. It took a couple of steps, but that allowed me to solve for x. Plugging x back in easily gave me the value for y. And again, I finished my problem by explaining what this means. Mr. Thornburg should mix 60 liters of 6% hydrochloric acid with 30 liters of 12%. I know today's lesson is pretty challenging, but I think you guys are capable of doing well, so do your best, come to class, and we'll see what we can learn. Have a good day.